Three. Okay. Okay, good afternoon, everybody, and welcome. It's my pleasure to introduce our speaker, Professor Ricardo Carretero. Ricardo has been at San Diego State since 2002. He's a member of the Nonlinear Dynamical Systems Group and professor in the Department of Mathematics and Statistics. He has a lot of interest in dynamical systems, nonlinear wave propagation, Bose-Einstein condensates, and various things, chaos, and so forth. He has a very interesting talk, and particularly today he's going to give us an interdisciplinary view on this topic. And I wanted to take a few minutes of his time to talk to you about a program in the Computational Science Research Center that we have currently, and particularly why this talk is timely for us at the moment. So we were recently funded by a National Science Foundation award under the STEM scholarships program. And under that funding, we have implemented a program with an acronym ASICS, Academic Support and Scholarships for Interdisciplinary Computational Scientists. The project directors on this are myself, Professor Castillo, and Professor Dustin Thoman in the Department of Psychology. So the overall goal is that we want to support graduate students. This program offers scholarships of $10,000 a year for 2 years to supplement what students get from teaching and graduate assistantships. But the goal of that is to attract students into projects and work with faculty to become interdisciplinary computational scientists and engineers. So the interdisciplinary component is the key to do that, right? And so in terms of the program activities, our goals are to increase awareness among graduate students of the needs, challenges, and opportunities in interdisciplinary research, and particularly interdisciplinary computational science and engineering. And to that end, we plan to offer a number of workshops and training activities for students, career exploration, networking events for students for such internships in industry, government labs, and academia. And CSRC for a number of years has been doing professional development workshops in helping graduate students polish their skills in various things, but also to be more effective in the studies, research, and future careers, right? So we just rolled out the application. We got a first batch of applications. We had an initial due date of September 15th. We still have a few open slots, and we're still looking for good candidates. So if you're interested, please do look at the CSRC webpage. There's a link to it, and this presentation also has a link to it. We'll send it out again if you're interested, right? So we have a number of activities planned, and one of them is to have a number of seminar speakers in this topic, but highlighting the interdisciplinary nature of research. And so to that end, today is one of our first presenters this semester, Professor Ricardo Carretero. And without taking any more time, Ricardo, it's all yours. You can share your screen.
Good afternoon, everybody. Thanks for being here. A little disclaimer, since this is part of the interdisciplinary push that we're trying to do at the CSRC, I am presenting something that is not completely new, some of my newer things is not that interdisciplinary. So I decided to do something that is not that new, but that it has a nice feel to the interdisciplinary motto of the center. So I'm gonna show you even movies of things that you will see in nature. We are gonna see a little bit of physics. We're gonna see a little bit of math. We're gonna do a little bit of numerics, all of that together. So I hope that this gives you kind of an idea of the interdisciplinary nature of some of the work that some of us are doing at the center. Okay, so let me just give you a summary of the things that I want to talk about. Just want to mention something about the subtitle. So it's an interdisciplinary view on vortex rings, nature physics, and computations, or how to be lazy. So I will explain what I mean by be lazy, but it's in a sense, try to use the math and the modeling in order to reduce a very large, complex, dynamical system to something much simpler. And that's kind of part of how I have been doing my research for the past 15 years or so, is try to follow certain patterns, be soliton vortices, some sort of coherent structures in a spatial-temporal system. So instead of just describing the full spatial-temporal system, just try to describe these elements, these jumping beams and their interactions. So we're gonna see some of these things as we go along in this talk. So a brief outline, I'm gonna show you a little bit of what vortex rings are. Unfortunately, because we're going to do this online, we're not going to be able to use my demo. I usually start shooting people with my vortex ring gun, but I'm still going to show you plenty of examples in nature. Then we're going to go to the application that I have in mind, that it's Bose-Einstein condensation, but in more general terms is a kind of a playground for fluids without viscosity, so superfluids. So I'm going to be kind of meddling between these Bose-Einstein condensate world and superfluids, and I'm going to show you what is the connection between the two and what is the model that is behind that is the nonlinear Schrödinger equation. I'm also going to show you some interesting numerical methods that we developed in order to make all the simulations that we're doing. It includes high-order complex schemes, a new set of boundary conditions specifically designed for nonlinear Schrödinger type equations, and also the GPU implementation. And then we're going to use those tools to study certain dynamics of these vortex rings. So we're going to do scattering, leapfrogging, some reduction of the dimensionality of the equations of motion that I'd like to share with you. Before we do that, I would like to thank my collaborators. So front and foremost, my two Greek collaborators, Panagiotis Kariakis and Dimitri Franziskakis. They are a big drive to these, not only multidisciplinary, but also multi-author, many people involved in this. And also the experimentalists, because after all, I'm actually trying to do this interdisciplinary science. So I'm a mathematician, an applied mathematician, but I love the physics because I have a background in physics, and all of this has to be applied to some real system in the end. So we have been talking to experimentalists for a number of years and try to understand the experiments. Not only that, work in tandem with experimentalists to actually understand what they're seeing and maybe plan. So kind of one of my biggest achievements, I will say, is not just maybe getting a grant, getting papers published, is now experimentalists come to us to tell us, what do you think we should be doing in the experiments that it's actually cool, will be transcendental for the community. So that's kind of the feedback approach from this multidisciplinary aspect, to talk also to the people that are down in the field doing these experiments. So that gives me enormous pleasure to have this collaboration with the list. I should mention that most of the work that you're going to see today is due to a former student of mine, Ron Kaplan. I think he's in the audience right now. He's now at Predictive Science. He's doing cool work there. At some point, maybe we could have him over and talk about the stuff that he's doing there. Also, part of the work that you're going to see was work with Jack Talley, was also a grad student of mine. And I have also a co-host of students that are working with me in the topics of fluids, superfluids, or bosons and condensates, and also some recent graduates that have also helped along the way. So the items or the building blocks that we're going to be working with are these vortex rings. They have a large history of being produced and being understood in some sense, and it's kind of easy to produce them. We're going to show them a few videos on to produce them. Here we have one of the first papers, reference to one of the first papers where people were trying to describe how to make these vortex rings in a kind of a clean way. So you have a drum. At the end of the drum, you have a membrane. You fill the drum with a certain gas, smoke. Then you heat the drum on the back, and that creates a flow that goes out through the aperture. And as you go through the aperture, because there is a hole that is smaller than the drum, that creates a shear flow. That shear flow creates a rotational that has a cylindrical symmetry around the aperture, and that creates these smoke rings that probably you have seen when people play with smoke rings and things like that. So let me show you a few examples of when you can see this in nature. So this is a funny example. It was there in the 50s in Times Square, actually an advertisement for the cigarette Camel. And there was a machine in the back that was producing smoke, and there was a drum, and the drum was hit on the back mechanically, and they were creating these huge vortex rings in the middle of Times Square. At this stage, I don't even know if this picture is real or it's a fake where they superimposed vortex rings, because I've seen actually videos of these advertisement, and the vortex rings were not as clean as you see them here. And the point is that these vortex rings are going to have stability, but not completely impervious to perturbations and to be destroyed by the environment. So this picture was taken maybe in a very, very clean night when there was no wind whatsoever, and they were creating these vortex rings out of smoke. Or maybe that's what I think it is. Maybe it's a fake, but just to show you that they were doing these smoke rings back a few years ago to show people and promote smoking a few years ago. These vortex rings appear in quite a few places. So this is a museum somewhere in, I think in Denmark. They are creating this on demand, just part of the museum exhibit. Through the chimney, they create these vortex rings. You will see also vortex rings are usually created when people smoke. Actually, these guys get pretty good at creating on-demand vortex rings and make them interact. They push them, they twist them. So you can see that they are sturdy in a sense because they don't get destroyed that quickly. But as they interact, as you saw, they're two interacting, they actually merge and they do get destroyed. Not only they being created by people smoking, you can actually see them in volcanoes. So this is one smoke ring that was left out by a volcano. This smoke ring went up maybe a couple of kilometers in the air. It has a couple of 100 meters in diameter. And as you can see, the smoke ring, it's stable, it's moving, it doesn't get destroyed, it's advancing. We were going to talk a little bit about the velocity of these vortex rings because they do have an intrinsic velocity. And I'd like to show you a little video. So hopefully this will play also with the sound. Actually, can you hear the sound?
Not very well. I think you may have to share your computer sound with it.
So there is a way to also share sound.
Yeah.
All right, if that's the case, if the sound doesn't show well, then forget about it. I'm gonna play important parts of the video. So this guy is shooting a vortex ring, and he basically destroys this house made of straws. So he's paraphrasing the story of the pigs and the wolf, that we can just bring down the house with just putting air into it. So you can see now how the vortex ring destroyed the house. And then he went to a house made of wood. I just skipped a little bit of the video. And I want to show you the last bit where he shows how the vortex ring is going to be going against a house of bricks, in quotes. So you can clearly see that these vortex rings, they also carry some momentum with them. So they also are energy carriers. So that's also a nice feature of these vortex rings. You have animals, humans that can do it. For example, you can do this. I have tried to do this, and in the swimming pool and in the ocean, it's not that easy to do, but once you get them going, they are pretty symmetrical and they go very nicely. Belugas are also able to produce these vortex rings. And something neat that you can see about these rings is that they have certain type of oscillations. Those oscillations can also be understood. They are called Kelvin modes. Whales produce also vortex rings when they blow the air through their blowholes. So it's interesting. It's unclear if they do it on purpose to create bubbles that are a little bit more ordered in order to, for example, sometimes they use bubble nets, the whales, to try to enclose fish so another whale can go in. So maybe that's one reason they create these vortex rings bubbles, so that it's going to be more sturdy than just creating a net out of just small bubbles. And the one that I like the best is these dolphins. And you will see a few things about these vortex. For example, this is a very highly perturbed vortex ring. It had a very nice shape and it's oscillating. And they're very sturdy, as you see. They can even be broken down and be separated. In this case, it's air inside liquid. The previous one that we were doing was gas, meaning smoke in another gas. So provided you have two different fluids or gases, you could create this. So very interesting dynamics. And you see how it got destroyed because they do not hold their stability forever. So you can see there are many systems in nature where these vortex rings appear. The application that I'm going to be interested on is bosons and condensates. I'll explain in a minute what a condensate is, but this is an example where the experimentalists were able to create a condensate. And they created a condensate and separated two bits of the condensate, the top part and the bottom part, by just changing the phases. So you created an interface that is separating these two different phases. But it turns out that because of the geometry, this plane that is formed is actually a planar dark soliton. It's actually unstable to perturbations. And it starts to wiggle and this gets destroyed, and it gets destroyed towards a beast that has more stability, in this case, a vortex ring. And you can see the vortex ring here by the two views, the side view and the front view, because you see these little hole, and this little hole, because these are projections of the condensate. So if you have a ring like this and you project down in one direction, you will see two holes. And if you project in the other direction like this, you will also see the two holes. So as you can see here, this is an experimental realization of these microscopic vortex rings in this Bose-Einstein condensate. And what you can see here in the bottom, it's a simulation of the same system, but where you can actually grab from the simulation, you can actually get the structure very nicely in 3D of the vortex rings, and you can produce many of these vortex rings through these instabilities. All right, so let me just very briefly introduce the topic of Bose-Einstein condensates. They were predicted almost 100 years ago or 100 years ago by Bose and Einstein. Experimentalists got the Nobel Prize not until 2001 because it took a long time to be able to produce cold enough temperatures to produce the condensates that they were produced in 1995, and that led to this Nobel Prize in 2001. And these condensates are dubbed the fifth state of matter after the gas, liquid, solid, and plasmas. And in a nutshell, this is how it works. If you have a collection of particles and you lower the temperature is connected to the vibrations in the system, to the kinetic energy of the system. The kinetic energy has the velocity on it. So as you're reducing the temperature of these particles, you're basically reducing the velocity of these particles. And as we know, there is a duality between the quantum world and the classical world. And the properties of the quantum world are given primordially through a wave that is associated to particles that is called the de Broglie wavelength. And that wavelength, the de Broglie wavelength, has the momentum in the denominator, and the momentum has the velocity in the denominator. Therefore, if the velocity goes down, this quantum property of the object basically increases. So the wavelength, the de Broglie wavelength increases. So what happens when this quantum property becomes large enough so that the mean particle distance between these particles is of the order of these wavelengths? So there is communication at the quantum level, and all these particles of the system basically collapse to the same quantum state. So to speak, a condensate is nothing but matter where all the bits of that matter are coalesced in the same quantum state. So if you want, a BEC is what a laser light is just to just normal light. So laser light is not just monochromatic, it's not just maybe powerful, has a lot of megawatts, it can burn. But the most important part about a laser is that the photons in the laser are actually synchronized at the quantum level. And that's why a laser beam doesn't open up, because of this nice property of the particles, in this case photons, being synchronized. So in the same sense, a BEC has all these particles that are synchronized at the quantum level. BECs now are routinely produced around the world. There are hundreds of different labs that are producing BECs. I have worked with a few labs, but lately I'm working with 4 labs. David Hall and Andrews College, Anderson in Arizona, Engels in Washington State University, and Professor Daniele Sanvito from Lecce in Italy. So we're working with all these guys on their experiments. Some of the nice applications of the BECs is not just understanding quantum mechanics at an experimental and applicable manner, but also they allow you to manipulate matter at the quantum level. So that means that many experiments that are experiments or apparatus that are capped by some sort of quantum fluctuations. If you're able to have everything synchronized at the quantum level, you will be able to do much better precision measurements. So gyroscopes, in principle, at least theory-wise, if you're able to construct a condensate gyroscope, you have a improvement of 11 order of magnitude with respect to laser-based gyroscopes that are the state of the art right now. So it's huge improvements. Also, accelerometers, gravitometers could be helped by using these condensates instead of just normal matter or light. Also, something nice about the condensates, because of these managing of the quantum properties, is they could be also a potential candidate to be used as quantum bits for quantum computing. With all that, so it's clear that it would be nice to understand some of these quantum objects, and what are the objects that are created in these bosons and condensates. And that's where we're going to do a little bit of modeling and trying to understand some of the basic components of the condensates, of the basic structures. These are vortices and vortex rings. I'm going to explain a little bit about those. So these are the equations of motion that govern the condensate. As you see on the top, this is the nonlinear Schrödinger equation. The first term is the kinetic energy term. Then there is a potential. The potential is the one that holds the atoms. The atoms have to be held in a magnetic potential. You cannot put them in a container because the container is hot. And if the container is hot, it will heat the atoms, and then the condensate will be destroyed because you need very, very low temperatures of the order of millionth of Kelvin to produce the condensates, at least for atomic condensates. Therefore, the best way to create these guys is through a potential that is created through a magnetic field. So you basically have all these atoms to be levitating so they don't touch anything, and then you cool them off, and then you can create the condensate. The beautiful term of this equation is the third term. What I'm showing you here is that close to zero temperature, this collection of particles, because they all coalesce to the same quantum state, you can use what is called mean field theory to, instead of following each one of these entities on their own in a multi-Hamiltonian body theory that will take a bit of your computer to actually tackle. For example, Calvin Johnson in physics, he's an expert on dealing with these multi-body Hamiltonians, and he has to use pretty nifty mathematical and numerical tricks to deal with this very gigantic set of equations with all these particles interacting. In this case, we are presenting an equation that describes the whole condensate in the mean field. So we're just basically looking at the density of these atoms, and all the collisions or interactions between these atoms or particles are all embedded within this last term that is a nonlinear term. So there is an inherent beauty about this reduction. So I'm describing on average what happens to these bazillion particles in the system. In this average sense, I get a beautiful nonlinear term that has the mod square of the wave function. But the origin of my equation comes from quantum mechanics, and quantum mechanics is intrinsically linear. It's interesting that by doing an averaging at the macroscopic level of linear equations and linear interactions, you get a nonlinear term as an effective way of describing all these. And this nonlinear term is the one that is responsible for some of the stability properties and some of the most interesting dynamics that you can observe in bosons and condensates. So if you're not familiar with quantum mechanics and you do not like to think about wave functions like you have here in phi, just think that phi, it's a complex field. It has a real and imaginary part. These real and imaginary parts are all the time rotating because there is a frequency to the system that has to do with the energy. Higher the energy, higher the rotation between the real and imaginary parts. But if you don't want to talk about that, just do the mod square. And the mod square is basically the density. And this is the measurable that my friends from the experiments can actually measure. Okay? So the theory has this quantum mechanical complex object that it's a complex field, real and imaginary. Complex in the terms of real versus complex, not just complex because of complexity. And it can be measured through the wave function's density through the mod square. So There are several ways that you can set up the experiments. You can set up an experiment when you trap all the atoms in a way that it's almost spherical. So in the three directions that you're seeing in these magnetic field, they're more or less the same strength. So you have kind of a ball. You can also have one of the directions of the trapping to be highly confining. So if you very highly confine one direction and the other two directions are kind of loose, you end up with having what is called a disc-shaped condensate. So you basically have a two-dimensional condensate. Or you can have two dimensions, two transverse dimensions to be strongly confining, and one, the third last direction, to be weakly confining in such a way that you have a one-dimensional condensate. So there is also another inherent beauty about these condensates is that the dimensionality of the system, the external potentials, they can basically be feasible almost any way you want. So it's a beautiful playground to do applied mathematics, because basically you can get almost any dimensionality, any potential that you will love to have. In this case, I'm going to be talking about a two-dimensional BECs, and then later into three-dimensional BECs. So let's talk a little bit about the intrinsic property of the Schrödinger equation or quantum mechanics. The point that I want to make here is that whatever many atoms you're trapping, there is going to be a real and imaginary part that are attached to the system. This is going to be important when I'm going to be talking about boundary conditions. Because usually, if you have this system to be not just the particles localized, but extended, you're going to have that the boundaries of the system are going to be oscillating. And this is going to create lots of troubles to set up boundary conditions. However, if you're at the stationary steady state, you see that the black curve here is just the density, that's the observable. So you can see that the mode square is actually fixed, but the real and imaginary parts are still oscillating. Okay? So when I'm talking about a steady state, it's a steady state where I'm actually talking a steady state about the mode square, because there's always this rotation of the real and imaginary parts through this intrinsic energy, or what is called the chemical potential, or the frequency of the system. All right, so if you go to 2D and you try to find the building blocks or structures that are the most sturdy, the most prevalent in 2 dimensions, they are vortices. These vortices can be thought of a solution such that the wave function is separated in terms of the, so let me just show here, in terms of the radial part and then a phase. This phase has 2 components. One is this one that is just a temporal frequency. That's the temporal frequency that you saw on the previous slide that makes the wave function to have the real and imaginary parts just rotating in time. So forget about this for the time being. The most important term is this one. So I'm going to have a wave function such that it's going to have a radial part, and it's also going to have a charge with respect to some, the center of the vortex, so that M will tell you how many times the phase is going to be wrapping around the center of this object. So M intrinsically here has to be an integer, because if M is not an integer, then I will violate the continuity of the solution of the equation. So it's interesting that just from the point of view of describing these solutions, I'm going to have discretization of the charge of the vortices. And you were familiar with quantum mechanics. That's the word quantum that comes from it, quantized. So here I'm going to have vortices that have a quanta of angular momentum described by this charge M. That could be positive or could be negative. And if you just insert these ansatz into the nonlinear Schrödinger equation, you end up with this ordinary differential equation with boundaries, what is called a boundary value problem. One of the interesting bits, and sometimes the hard bits, is that this boundary value problem does not have an exact solution. So even the most straightforward building block of solutions of the 2D NLS doesn't have an exact solution. Nonetheless, I can still computed solutions. So you can compute its solutions. So here are the solutions that you can see depending on the charge. So if the charge is 1, you get a vortex that is thin and narrow. A vortex of charge 2, it starts opening up because it has more angular momentum. Vortex of charge 3 opens even more. And here I'm going to show you how the solution looks like from the top. On the left, you have the phase, and on the right, you have the density. The density is stationary, steady state. The phase on the left, you see that it's rotating, and it's rotating because I have this frequency omega that is actually making this thing to rotate. And this one is a vortex of charge 1, because as you see, there is a single phase jump as you go around the origin of the phase. So you go from red to blue just once. If this was a charge blue, vortex of charge 2, you will go from red to blue once you do just one turn. Okay? And one of the interesting things is, okay, you have these beasts, so you can talk about the inherent stability. I'm not going to do that, but these are very stable, and it has to do with their quantum properties. Well, maybe 10 seconds on that stability. Since these beasts are quantized in charge, there is no way to dissipate charge. A normal eddy, a normal tornado can have any angular momentum. So that's the way a tornado will dissipate. It will dissipate the energy because the angular momentum will just go down continuously. Here you cannot extract angular momentum because the angular momentum is quantized. So there is no continuum way to go from charge 1, i.e. one vortex, to charge 0, i.e. no vortex, in a continuous way. So because there is no way to go continuously from 1 to 0, these guys have to be stable. You cannot destroy them. They're topological structures. So that's amazing. And this gives these guys this structural stability for their existence. And you can start thinking what happens if you have 2 of these vortices put together. So if they are of the same charge, they start rotating around each other. If they're of opposite charge, they start just traveling parallel to each other. So these are building blocks in 2D. What happens if now we try to extend these solutions to 3D? So imagine that I have now a 2D vortex that is just extended over the third direction, just by copying the same solution over the third direction. So this is what you get. So you basically get just a twister, just a tornado, a tube of vorticity. In this case, I placed 2. And you can see that I placed 2 of these twisters, these 1D twisters. And because they are of the same charge, they're actually going to rotate each other around each other. The system here is not homogeneous because they have a very elongated trap. So they have a more interesting kind of dynamics. In the bottom figure, this is kind of an emulation of the way that I told you that experiments create vortex rings, in such that you create 2 parts of a condensate with different phases. So in the bottom picture, you see 2 different phases of the condensate separated by a wall. So this is a dark soliton wall. And as I start running this simulation, you will see that that dark soliton wall is unstable, and it's going to give rise to 2 of these tornado tubes, okay? And these 2 tornado tubes, as you can see, they actually travel parallel to each other because these tornado tubes, they are of opposite charge. And they are of opposite charge because I started with a dark soliton wall. That dark soliton wall had no angular momentum, so it had to create beasts that their sum had the same angular momentum that I started with. And that's why it created a plus and a minus. So the total amount of angular momentum is 0 because you have a plus and a minus, okay? But you saw the basic structures that are just vortex lines, in this case, vortex tubes, that are happening in 3D. So now the question is, what happens if I grab one of these tubes and I just close the loop of this tube on itself? If you do that, you get what is called a vortex ring. You can actually find these as exact solutions, numerically exact, because there is no functional form for them, but you can actually predict that these guys, they do exist. They're steady states in a common ring reference frame. And the reason that these vortex rings cannot exist in a stationary frame, meaning that they always have an intrinsic velocity, is it because suppose that you have the ring like this. So the opposite sides of the ring, they basically see each other as something that rotates in one direction and the other one that rotates in the other direction. Therefore, the opposite sides of the ring, they just see each other as just very tiny, small lines that have opposite charge. And as we saw in the previous runs, the opposite charge lines, they will just try to run parallel to each other. And that just happens all along the circle. So because of these contributions, these vortex rings will always have an intrinsic velocity. And intrinsic velocity can actually be computed depending on the parameters of your system, and more particularly on the radius. In this case, the radius is d, c is the velocity, and as you see that as d goes down, their velocity goes up because the ring becomes smaller. As the ring becomes smaller, the interaction between sides becomes stronger, so they actually push each other to run in parallel faster. So a tighter ring will go faster than a loose ring. All right, so these are some of the basic properties. Now, let me spend some 5 to 10 minutes on the numerics that we employ and some of the techniques that were involved in these numerics, as you saw there. And again, I need to acknowledge my former student, Ron Kaplan, because he came up with most of the stuff that you're gonna see here. So we want to try to do parallelization because we're doing this in 3D. And if you wanna do parallelization and you wanna describe this system in 3D, you need several things to happen. First, you need as few points as possible, because if you have few points as possible in your mesh to discretize your system, then you will be able to run the computer faster. You want to have a method that is as high in accuracy as you will want, so that, again, you can have less points. So if you have a technique, for example, just like finite differencing, you just take first nearest neighbors in order to actually work out the Laplacian, you get a second order technique, right? Well, that's okay. If you want a higher order, just go for more neighbors. So for example, you can have 5 points stencil to compute the Laplacian. And this is a fourth order technique. But there is a problem because now I'm sharing 5 points. That means that if I'm gonna be subdividing my domain to do parallel computation, then I need to now send to my contiguous subsystems more information. And in 1D, it's okay, because in 1D, you share just 1 or 2 points on the boundary. But if you go to 2D, then you need to start sharing planes. And if you go to 3D, you need to start sharing sets of planes of neighbors. That means that there is a lot of communication between the different subdomains. So you like to avoid having many points in your stencil. So I have a competing thing here. I want higher accuracy, but I don't want to share neighbors. So what you can design, it's a high order compact scheme. So I can still design a fourth order scheme with only sharing 3 points in my stencil by doing the 2 steps. So instead of doing 1 step with 5 points, I do 2 steps with 3 points. And because of the bulk of the problem of the computation goes into the communication between the different subdomains, this technique, although I'm doing twice as many computations, because of the less sharing with my neighbors, it becomes faster. So we implemented this higher order compact scheme. It's here given in a nutshell, and we proved that indeed it's second order and it works pretty nicely. All right, the next thing that we develop is we develop specific boundary conditions. The simulations that you saw there, you saw the vortex ring, but what you have to take into account that the vortex ring is basically empty. So you have an ocean of condensate, and then you have the ring that is basically just the emptiness. The same as you will have the tornado. Inside the tornado, you don't have anything, and outside you have all this mess. So in here you have the Bose-Einstein condensate, and you have the emptiness of the ring inside. So basically you need non-zero boundary conditions because the condensate has non-zero boundaries at the edges. So contrary to the case of a bright soliton, so this is the example of a bright soliton, where you can actually set the boundary conditions to 0 at the edges. But the condensate that we're treating, where you have vortices and vortex rings, is what is called a repulsive condensate, and you need to have the boundaries that are non-zero. However, if the boundaries are not 0, because there is this rotation between the real and imaginary parts, in this case, the blue and the red that you see on the screen. And also, as soon as you start making these structures, the vortex ring to move, then you have plane waves that are associated with these movements. So you have at the same time rotations due to the frequency of these real and imaginary parts, and then you have translations of these plane wave solutions. So what my equation is describing is a complex field on these red and blue bits. And in reality, what is fixed is the density. So you have to fix the density where the density is a nonlinear function of your actual fields. So I cannot set Dirichlet, Neumann, or anything on the blue and the red. As you see, it's complicated. I need to have Dirichlet on the black, but the black is a nonlinear transformation of the blue and the red. So we Ron worked out how to actually do this in a nice way. So we can set up a boundary condition that is on the mod square of the function, and it works really nice. And the movie that you just saw there, it looked almost like transparent boundary conditions, like the blue and the red were doing exactly what they needed to do, although we were fixing the density. And you have on the top there the reference for you. And in the end, it turns out that computing the Laplacian at the boundaries has to do with this formula that I have in the bottom, this specific implementation for the nonlinear Schrödinger equation, but it could actually be modified for other equations where you have a non-constant background field at the boundaries. All right, the third bit that I want to show you is the CUDA implementation, or the GPU implementation. So just to give you a sense of the timings, in order to create this simulation on the left, this is done in MATLAB, just doing finite differencing, and it takes around 3.5 hours to produce this simulation. Obviously, MATLAB is not the most efficient way to do things. You can actually compile, do a compiled version of this code. You can use an X code, or you can do a C code. So this will be just a serial computation, but using a compiled language. And you can take the time down to half an hour. So still a lot of time. If you use these GPU computations, these GPU implementations, you can actually do the same simulations with very little cost in just a very pedestrian NVIDIA card that costs, maybe this one doesn't exist because it's just way too old. Maybe you can get it for free if you go to some dumpster and then you can just collect it there, but it takes around a minute. So the beauty of doing the implementation using the appropriate boundary conditions, the high order compact scheme that we design with the GPU computations, is that we can do these 3D simulations almost in real time. And this took 1 minute, but I'm sure that if I use just a chunkier card, we could do now nicely on demand any sort of simulation on 3D with this type of accuracy in real time. That's kind of mind-blowing, at least to me, that I was starting to do these 3D simulations, I don't know, 20 years ago, that you can actually do real-time integration of these system. It's just pretty cool. All right, so in the last 5 minutes, let me show you some of the applications. Before I go that, if you're interested in these codes, they have all the bells and whistles. They have the higher order compact schemes, the boundary conditions, but more specifically the GPU implementation. You can go to this website that Ron mounted, where all the codes and examples are there, and it's called NLSE Magic for nonlinear Schrödinger equation, and magic because it's magical, but you can see that where the acronym comes from, it has to do with multidimensional MATLAB-based GPU, blah, blah, blah. So it's a nice set of tools that you can download for you. So let me show you some of the now interaction between the beasts. We already talked about vortices, their interactions. We saw just lines of vortices also interacting. Let's see what happens if you have now these vortex rings interacting. For example, you can have vortex rings that are just colliding frontally, and if you have them colliding frontally, what you happen is you basically get this, you destroy them, and basically all the angular momentum is destroyed because you have this plus and this minus that they just interact and they just destroy. That's what happens if you have a head-to-head collision. If you do not have a head collision, but you have a certain offset, you get these beautiful dynamics where half of the vortex ring of one ring is attached to the other half of the first one, and then the scattering after this, you have two vortex rings that are highly perturbed. So you see these Kelvin mode oscillations, but there is a definite angle that you can see that these things are actually scattered through. All in all, you have three types of scattering for these vortices. You have a head-on collision, like example A here, where you have destruction of the vortex rings. You still have some sort of wave that goes out in an angle, but that wave is not carrying angular momentum. Then you have the case B, where you have more like a marriage, where they exchange bits and pieces and they get scattered at an angle, and then you get two nice vortex rings as a result. Or if the separation is a little bit larger or comparable to the size of the vortex ring, you have what I would call flyby scenarios, where just barely touch each other and they just go out. And if you do many simulations of this system, you realize that the most important parameters to measure is what is called the impact parameter. So the impact parameter is basically what is the relative distance of these vortex rings where they're going to collide, normalized to the radius of the rings. So we did many simulations, and as you can see here, the angle of scattering, depending on the size of the rings, as soon as you just normalize the impact parameter or the relative distance, you can have kind of three stages, or three regimes. One regime is when they are very close to each other and basically they annihilate each other, and you have just these kind of shock wave going at an angle that can be described by this very simple formula. And in the middle range is when you have this mixing. So it's interesting that all these very complicated dynamics can be summarized by just checking how close, what is their size, how close are they going, and then you will know what is the output after they mix and go out at a certain angle. And finally, there is the tail here at the end between 2 and 3 for Q over D. It's just a flyby scenario that decreases exponentially because of these guys are less and less, they interact less and less because of the distance between them when they interact, right? All right. The other specific case that I wanted to talk to you about is this leapfrogging case. This leapfrogging case has a very nice shape to it. As you can see, there is a vortex ring that goes inside the other one. It will take me a couple of minutes to explain why this happens, and has to do with one, when it goes in, pushes the other one out, because there is this rotation between the bits, as the same as I explained why a ring has to have an intrinsic velocity. So there is a very hand-wavy way to see why this solution will exist, okay? But the most important part is there a way that we can actually describe this system in a way that we reduce the original, very complicated numerics that we're doing to something much simpler? And what we're gonna do here is try to do a reduction to an effective particle approach. So imagine that these vortex rings just have two properties, or few properties. The most important properties is basically the radius, the position, and also the angle. So all these geometrical properties that is describing a vortex. Obviously, they could actually have some sort of excitations. You can put more and more degrees of freedom if you want, but let's just have the simplest possible case where you have two vortex rings that are collinear, so they share the same axis, and they just have a position Z1 and Z2, and each one has its own radius. So this should be able to be describing the previous dynamic that we saw. We only need to know where the vortex ring is in this position and what are the radii. So in some sense, we are reducing the original system that was a very complicated PDE that we were integrating into just a few parameters for each of the vortex rings. In this case, radius, position, angles, or if you want to get funky and fancy, you can do undulations like Kennedy modes as well. So if you try to do the whole fluid and you want to do integration of your fluid, then you need to do this discretization. In this discretization, we are going to be using hundreds or thousands by 1,000 by 1,000. So we're going to use 1,000 cube nodes. Instead of doing that, I like to bring it down to just a very few equations where each particle, each ring will be just described by its position, its radius, and its angle. So you have very few degrees of freedom. Therefore, I will be able to change a very complicated system with 10 to the 9 discrete set of points to just hundreds of equations. The way to do this is borrowing techniques that have been there for a while. And it's very nice connection between a nonlinear Schrödinger equation model and just an inviscid Euler model. And what you do is what is called the Madelung transformation. So you transform or you rewrite the wave function as just density and phase. The density is rho and the phase is phi. And if you identify that the gradient of the phase is the velocity, beautifully after you do a little bit of hanky-panky, you can actually rewrite the nonlinear Schrödinger equation as a hydrodynamic form into an inviscid Euler, meaning a fluid without friction. However, there is a price that you need to pay. The price that you pay is that there is an extra term. This extra term is what is called the quantum pressure. However, if you see the shape of the quantum pressure has the derivatives of the density. So if you're far away from a vortex, the density is flat. So if you are far away from vortices or vortex rings, i.e. if their interactions are far from each other, not full collisions, but just interactions far away from each other, then this quantum pressure term can be negligible. And if it's negligible, then you can think about this system as being equivalent to an Eulerian fluid without friction, a superfluid. So you can use, for example, the Biot-Savart law to describe the condensate. If you do that, you can actually describe the leapfrogging of the condensate. And this is the equation, the effective equations of motion that come out of doing this Biot-Savart law, where I only have ordinary differential equations for the radii and the positions. The first, the z is just the intrinsic velocity. The last equations, the last terms in both equations have the u. The u is kind of a potential that tells you how these two guys are interacting. The potential, yes, it's complicated. It's in terms of some sort of a Jacobi elliptic functions. You see that instead of just integrating this full three-dimensional system, I can just integrate these 4 ODEs for 2 positions and for 2 radius. And the results in a co-moving reference frame for this leapfrogging behavior are like this. So you can see that the leapfrogging that advances, if you just do it in a co-moving reference frame, you have just one vortex going inside the other one. You see these kind of closed shape figures. These are for different cases of different radii. There's a really nice match between the full numerics and the reduced numerics, the reduced system. And this is basically the message that I want you to take home, that if you apply these sophisticated mathematical techniques, you might encounter a much simpler, much more reduced in dimensionality system that you will be able to integrate and say many things about it, whereby the original system is way too complicated, too large to actually do anything but just draw some full numerics. These vortex rings can be actually done not only 3, there could be 7 or any number of them. And with that, I will close because I'm running out of time. And just to mention that we are in the process of trying to introduce now also the trap, because this could also be trapped. Find how the undulations of these Kelvin modes interact and other topics related to the experiments. So thank you very much for your attention, and I'll be happy to answer any questions.
Thank you, Ricardo. Nice talk. Questions for Ricardo?
guess it was so clear that there's no question.
I think it was so turbulent that there are no questions because it's way too turbulent.
On that note, thank you, Ricardo, and thank you everybody for attending the colloquium, and have a nice weekend.
Thank you.